Good morning, everyone. It's me back again from yesterday. You already know me. So today we'll talk about convolutional neural networks as opposed to we've already learned fully connected networks and we've already built models as well. So let's get started. So I am going to just give a brief introduction of what CNNs are. Not using any math, just general, conceptual introduction. I will then talk about why, why they're useful, why people use it, and then go a little bit into the technical background. So I'm saving. Actually, this talk is not very mathematical, unlike other talks, because I am not in a university. I actually work these days, so I'm not a theoretical person anymore. So I don't even know the math very well. So I wouldn't even know if you ask me difficult questions about the math. That would have to be saved for somebody else. But since I use them a lot, I use, this is what I do at my work all the time. I am pretty comfortable with them as a user, as a practitioner. So I would say I have better practical knowledge than theoretical. And hopefully I can give you similar decent, some practical, knowledge and tips and whatnot. All right. I've uploaded the scripts that I use for the lab and also to generate like examples and whatnot here. It's not up to date, but I'll update them as as we do the lab today and as I finish these lectures. But yeah, this will remain there in the future as well. So maybe we'll upload them. There's a NAAMII GitHub too. I don't know. Maybe we'll upload them somewhere else as well. But in addition to the Google Drive, I'll put them here in GitHub like forever. So yeah, you can like star it or whatever if you want to, so that you can or fork it, whatever. That's all up to you. Okay, so what are CNNs? It may sound like really like fancy and complicated, but it really isn't. It's not the television channel. We all know that, right? just in case people are confused. It's not the television channel. Let me just assure you. And so generally, yeah, if a neural network uses some convolutional layers, then it's called a convolutional neural network. Particularly like the more classical networks are built in such a way that the first many layers are convolutional and the last couple layers are fully connected, or in other words, we also call them dense. And the reason for that is it'll get clear as we move on. So yeah, so very simply, what are convolutional neural networks? If any of the fully connected network is replaced by convolutional connections, then it's CNN, all right, and not the new channel. I'll repeat myself. Okay, so we've seen this diagram maybe yesterday, maybe even before, too many times by now. So you all know the fully connected network. So let me just recap a little bit. We have the input, we have the hidden layers, and we have the output, which is the softmax. And can anybody tell me why we have a softmax here and not say the sigmoid? Does anybody remember from yesterday? Multiclass, wonderful. Wow, you paid attention. I am very impressed. And let me ask you a few more quick questions. So what is the dimensionality of the input to this neural network? 4, yes, correct. What is the dimensionality of the hidden layer number 1? Right, so what are we, so the weight here, the parameters from hidden layer 1 to, input to the hidden layer 1, what would be the shape of that matrix of the parameters? Can anybody tell me? 4 by 6, wow, wonderful. I'm very impressed. So you guys are doing very well this morning. I hope it continues. Yeah, so yeah, that's quite correct. It's 4 by 6 because it's fully connected. There are 4 inputs and they're all connected to the hidden layers. So in convolutional network, it wouldn't be so easy to say, oh, this parameter shape is 4 by 6. We need to do a little bit of it's still, there's a way to calculate it, but it's not obvious like that. And I'll teach you how to calculate the number of parameters. Yeah, so yeah, here, we have from 4 dimension, we're going to 6. And from this 6 dimension, we're projecting back to 4 and to 3 ultimately. So we can also think of these things as nonlinear projections. If we've heard of this term called projection, we talked about how matrices do projections in like in 2D geometry, right? We talked about Shashwat gave examples in 2 dimension. So here, these matrices are doing transformations and or projections, whatever we want to call them, in 4 dimension to 6 dimension. So yeah, we can even go from 1 dimensionality to higher and higher to lower, right? So when we're doing compression, we always go from higher to lower. So you can think of these as linear transformations. So yeah, in the case of fully connected, these connections and these parameters and these projections are very intuitive and easy to capture and discuss like this. With convolutional, you need a little bit of more nuance while talking about these things. But the idea is pretty simple still. All right. Any questions so far? Remote or local? Good. Yeah, everybody? Awesome. Oops, this is not moving. All right, so this is like a typical, diagram, network diagram of what, a lot of convolutional neural networks look like. This is a slightly more classical, like older one. I mean, a lot of the newer networks are much bigger and it's not easy even to show it in like a page like this, but this is a classical and quite like popular one. This used to be one of the most popular, like most successful at that, when it sort of came out. And one thing you may notice is also it has very simple, the architecture, at least the style is very elegant and simple. If you look at it, there's the images, the input size is 224 by 224. So let me ask you again, what is the dimensionality of the input to this neural network? Louder, please, somebody. Who has the answer? Sorry? Yeah, that is correct. It's 224 square. 224 by 224 is the dimensionality of the input. But the dimensionality of the first layer is also 220. Well, it's actually 224 by 224 by 64. So we need to account for that 64 as well. However, it's not like the linear ones. So just imagine if we were using like a dense connection here, what would be the number of parameters here? 224 square times 224 square times 64. I mean, that's just like crazy. That's billions, maybe even trillion. I don't know, but you can imagine why. That's one of the reasons, and I'll talk about it a little later as well. That people started developing different kind of connections than the fully connected. Anyways, this is a pretty typical example. We have as I mentioned, there are 5 convolutional networks and few fully connected convolutional layers and few fully connected layers in the end. And as the diagram suggests, after each sort of like stage, the dimensionality, well, at least the height times width of the feature has been halved. And that operation is called pooling. I don't know if you may have heard of it or seen it if you've done any experiments with these things. So yeah, this is a typical setup where as the network, as you go deeper in the network, the feature size, in terms of height times width, particularly with images, keeps decreasing like this in half, right? We go from 224 to 112 times 56 times 28. But the width, which is the number of features per at each sort of layer, keeps increasing. In fact, it's like doubling. You know, we go from 64 to 128 to 256 to 512, 512. Yeah, that's in the end we have 512. Sounds good. Any questions so far? Still introduction. I mean, I'm gonna go into the details of each of these things slowly, but yeah, this is a pretty typical setup, and particularly with the older, slightly more classical networks, this used to be, you know, the sort of like a very typical sort of setup. So okay, hopefully this works. Yeah, it's working. So that is, okay, let's spend some time here. That's what the convolution operation looks like. So, you know, I imagine maybe the computer engineering people or the EE people are familiar with the term convolution, have done it. Who has done convolutions in their class? Okay, so in fact, one thing that's different about the convolution here and in signal processing is actually this. In neural network, they're actually doing cross correlation and not convolution. But if you remember from your lectures of convolution in your class, actually the cross correlation and convolution are quite similar. There's just a flipping, right? If you remember with convolution, you have to flip either the signal or the well, you have two signals. You have to flip you have to flip one of the signal. You remember that or not? Whereas with cross correlation, there's no flipping. So here, you know, when we're doing this in neural networks, we don't do any flipping. And the reason for that is because we're trying to learn the parameters appropriate for a layer, right? If a flipping was required, the filter itself would come as flipped. So there's no need to flip that filter from the very beginning. Does that make sense or no? Too confusing? So okay, to summarize, basically there's no need to flip, but we're doing cross correlation, but we still call this convolution. That's just nomen, you know, that's the term people use, and it's a slightly wrong name, but it's okay. Everybody understands what's going on, and you should also understand. So don't get confused. So again, if you remember from signal processing, who can tell me what convolution does? When you convolve to signal, what happens? Or cross correlation, what is cross correlation doing? Anybody, any thought? So let's say we have this filter of this shape, right? 1, 1, 1 and -1, -1, 1 and 0. What sort of so when this cross correlation is happening, it's happening. Let's say we're just focusing at the top left sort of corner, right? And this is being cross correlated with, at the very first one, it shows 7, 2, 3, 4, 5, 3, 3, 3, 2. And then we do element-wise multiplication and sum it. And remember, we talked about element-wise multiplication maybe even yesterday or the day before. In signal processing, again, the technical term is Hadamard function or something, but it's not important. But point being, yeah, this convolution operator is applied here, and at the same size, the part of the image. And in the left, imagine we have this image. It's a really small image, but this is the image. And on this on the middle, we have the convolutional operator or the filter kernel. There are many terms used for this. And then we do element-wise operation, right? Few things to notice. This is a local operation. So the very first output 6 here in the top right, top left. Can you see my cursor? Yes. In the top left is not influenced by this 4 down here, or this 5 down here, or this 8, 4, 7s down here, right? This 6 is influenced only by 7, 2, 3, 4, 5, 3, and 3, 3, 2. Does that make sense? That's why we say convolutions are local or sparse operators, and the connections are sparse because if this was a dense connection, this output would have been connected to all the inputs. But here, because of the way we do convolution, this output 6 here is only connected to the 3 by 3 segment on the top left. Does that make sense? Yeah. Now let's go back to the second point, the same filter is applied at all locations. As you can see, this this animation just keeps moving across the image, but the kernel stays the same. And it's essentially what we're calculating is how this image responds to this filter. And can anybody tell me what this filter is, what this filter resembles, if from signal processing, or if you've seen this anybody else? Sorry? Yes, yes, that's correct. What kind of edges? Vertical edges. Wonderful. Yeah. So yeah, this filter, obviously this is a made up example, but if you actually look at your outputs of your neural networks, especially your early layers will have at least some sort of edge detector kind of filters like this. And this edge detector is doing precisely that. It's finding points where the values in the left are bigger than values on the right vertically, because there's one and there's -1. So wherever and this is essentially doing edge detection, right? What sort of other operations could we do? Again, from signal processing, right? We know what sort of other filters do is very common, like sorry? Diagonal, triangular. I'm not quite sure about that. I'll give you another example, which is quite popular in signal processing. Blurring. Did somebody say blurring? Gaussian. Yeah, Gaussian blur. Exactly. That's another example that's quite common. What is Gaussian blur used to do in image processing or signal processing? Smooth, right? Perfect. That's the answer I'm looking for. A Gaussian would just smooth out the image, and it would reduce noise. So your network could conceivably learn smoother as well. But this one, I handmade this, not me actually. I copied this from the internet. But some guy hand coded this. But yeah, so essentially the point is different filters with their different weights respond to different attributes of the signal, right? So and do different things to the signal. An edge detector will respond to edges. A Gaussian, blur doesn't necessarily quite respond to any particular thing. It just sort of like smooths everything, right? There could be a horizontal edge detector as well. This is just a vertical. So this is the idea. Like, but obviously, in the classical signal processing world, image processing world, your engineers and scientists would sit around and craft these filters, or like banks of filters like this, and then they would do their image processing and they would build their features in the images. But in the whole idea of neural network is you don't like hand code these, and the network learns it by themselves using back propagation and all the nice optimizations that we heard, I think yesterday, maybe the day before. I think there was talks about optimization as well. So yeah, this is actually the pretty crucial component to understand, and I hope this makes sense. Yeah. All right, let's any questions so far? So does everybody understand convolution? Yes. Question. I don't see we have. I don't think. I don't. Yeah, you can just say, and I'll repeat it out here for everybody. Yeah, that's a very good question. So the question was, is there any particular technique while choosing the filter? So so this is exactly what I was trying to say. In the classical realm of image processing and computer vision, engineers and scientists would sit around and try to come up with really clever filters or ways to extract interesting signals out of your images, or signals, interesting features, attributes. But with neural networks, you don't actually make these filters. The network learns it by themselves, by optimization. So you can control, let's say, the size of the filter, and you can do initialization of the weights. There's some different techniques, but you don't control what happens afterwards. It just learns. It learns whatever gives a good performance. Does that answer your question? Any more questions? Yeah, all right. I think we can move on. Okay, so I think I've actually already given a lot of motivation for why, but let me again go through it again, because I think it's pretty like crucial to understand some of these things. So for me, I mean, again, my practical understanding is that as we talked about earlier, right, with the 224 by 224 images, like the size of, if we made a dense connection for that, we got 224 to the power 4 by 64. I mean, that's just insane, right? Like you'll never be, if you have all these sort of connections in your network, you'll never be able to learn anything, at least in a reasonable amount of time with limited resources. Like, when I trained some of these models for demo today and for the lab, I was able to do it in like a small, like a desktop computer. But you would need like crazy, GPUs and cloud, resources to do, learn even the most simple network if we had so many parameters. So yeah, so that's why, one really like big advantage of CNNs is it uses significantly less parameters for sort of comparable performance. So with like smaller problems, you can get comparable performance, or the fully connected network can even be better. But with really complex, large problems, actually convolutional neural networks are obviously better. But let's say for like simple problems, you may have similar performance, but the size of the convolutional network is really really small. But when we're talking about the size of the model, we should not confuse. There are two things to consider. There's the total number of parameters, and there's also there's the total number of operations that we do. So the convolutional networks do have less parameters, but doesn't necessarily mean there's less computation. So we always have to remember both of these things. You may have heard such terms such as flops and whatnot to describe so both the size of the model and the number of operations, floating point operations that you have to do determines the efficiency of your model, like how fast it runs, right? So, but parameters being really less is good for training, and the number of flops being really less is good for testing during inference. If you're running your application real time, with like mobile devices, for instance, and you want to run inference on the device itself, you have to be mindful of both the parameter size and also the total number of floating point operations. Just remember these things. I should have written that down here, but you'll probably hear that come up more often. So CNNs use sparse local connections, and it's a form of implicit regularization. So what does that mean? So again, if we know from signal processing or some other more classical examples, remember how like in linear regression, who has heard of the term L2 norm regularization or L1 norm regularization? Okay, can somebody tell me? All right, tell me, yeah, here. Okay. Is that mic working now? Can you?
No.
Okay, yeah. Somebody who has an idea, maybe in the back, just behind you.
Theta to the means theta parameters and adding it to the loss function.
Yeah. So L2, yeah, L2 norm, and particularly the L1 norm regularization, if you've heard of it, what it does is it regularizes the absolute value of your, it sort of like tries to reduce the absolute value of your parameters. But what it leads to is it leads to sparsity. So a lot of your parameters end up becoming zero. So and this is a pretty these are pretty common forms of doing this thing called regularization. um, and why is regularization important? I mean, that's probably a whole another lecture, but so oftentimes when we're solving these sort of problems, we have the total number of parameters start exceeding the total number of data points we have. So we call these sort of problems over complete problems, where the possibility of the solutions is like really, really large, and we may not have a good way to choose what a good solution is, good solution space is. So we come up with these ideas, these techniques where, oh, then maybe if there we maybe a good solution space is where the norm is really small, or the parameters are really sparse, which means a lot of the weights are zero, and only us important ones, significant ones are one. So this is very common themes and ideas in not just machine learning, but your traditional signal processing and computer vision as well. And making a network convolutional by design, you're already making a very strong implicit regularization, and you're making this this idea, this I think Bises I talked about in the first day, an inductive bias about the structure of your data and the structure of your networks. Again, yeah, it's but to practically, why is sparse, why are local connections important? So the way to think about it is in terms of the hierarchy of the features, right? We saw in the previous example, the first layer, first layers will just learn to do like edge detection or Gaussian blurring, vertical edges, horizontal edges, Gaussian blurring. Now, these are very simple things, but I don't know if somebody was trying to say diagonal, triangular stuff, but maybe to learn somewhat like random kind of like filters as well that we wouldn't be able to come up with, that have elements in the diagonal, or like I'm not sure what they were trying to say, but yeah, it'll learn all kind of filters. And your first level of features will be these, just responsive to edges, and will be smooth and so on and so forth. Then in the next layer, you'll start getting more and more complex features. At that point, maybe it's not just edges, it's responsive to like curvatures. It's responsive to you maybe one set of filters are responsive to like convex shapes, and one set of filters are responsive to concave shapes. Maybe some filters are responsive to circles, some filters are responsive to rectangles, right? And in the next one, it can get even more complex. Now imagine you're doing let's say trying to classify, like in image, classic image example, like cats, dogs, things like that. At that point, your higher level of layers will start being responsive to things like the eyes, the legs, the head. And so the idea is you start building very local, like simple features. And as you like increase go deeper in the network and have hierarchical set of complex features, the features start both becoming global and also more complex. So you always build this sort of bottom-up approach of constructing signals. And these are, again, techniques used in sort of classical signal image processing and computer vision as well, and also inspired a little bit from how the human visual cortex works. Our eyes receive information, as light, obviously, and you're basically I forget the names, your cone and rod cells in your retina just fire up, and there are these hierarchies of neurons, and the first layer just respond to, oh yeah, there's some light in this, yes or no, very simple operations. Then as they combine and sort of go deeper and deeper, you'll have your brain will start making more good representations of the real world. Oh, there's a person, there's a dog. It's, as we have heard multiple times, the how the brain and our actual neurons and how that works exactly, and how the neural networks work, it's not exactly the same. In fact, there are a lot of dissimilarities now, but just as a a motivating example. And the last point is also quite important. We will see example of how this works, but essentially, we use this operation called pooling, which helps reduce we saw how the image sizes are reduced, and that gives us translation invariance. I will talk about that a little bit. I'll also examples of how that works. Okay, back to the famous EKZ data set from yesterday, which kept vanishing because I don't know what you did. But luckily, it didn't vanish totally. I still had it, so I have it here and add some examples as well. So I will just look at some examples again using this famous EKZ data set. You all know and did wonderfully yesterday, I imagine, in predicting the normal and abnormal classes. I hope everybody had greater than 90% prediction success accuracy. Again, for folks who are not there, just to remind you all, we have these EKZ signals, and EKZ are, these are generated by placing leads on heart of patients at hospital. You see these squiggly, these sort of things in a monitor usually. These are EKG signals, and obviously normal people have normal pattern, and sick people have sort of different weird patterns. And again, if we have, actually we do have a doctor amongst us, at least we had yesterday, but I don't know if he's here, but maybe he can, well, I don't want to put him on the spot, but but yeah, essentially, that's what it is. We have, and basically we are building classifiers to solve this problem, right? Any questions on this, particularly for folks who were not able to do lab yesterday? We've all seen EKZs in movies, how in Bollywood movies, I gave that example yesterday. Somebody dies and this goes flat for 2 minutes, but then the mom starts praying and they come back. Right? We're all familiar with it. All right. I don't think this data set has that kind of data, but it would be quite interesting if that was there. Okay, so yesterday I told you all to build fully connected networks, right? And if we remember again, roughly, we had the input and our dimensionality of our data was 1441. We all remember that yesterday, 1441. And then we had two hidden layers, sorry, with 100 and 200 nodes, right? 100 and 200 nodes, and we had our output. For the first problem, just the normal abnormal classification, we had just one output. But now we have a similar, roughly similar convolutional neural network where instead of dense layers, we have a convolutional layer and max pooling, convolutional layer and max pooling. Typically, when people say, draw out convolutional layers, they include both they sometimes include the convolution operation, the activation, and the max pooling together as a single block, because it's particularly with images, it's done so often that we consider these things sort of together. And yeah, here we don't even have, I haven't even showed the activations, right? Again, because it's so standard it's almost guaranteed that you'll have activations after like both a dense layer or a convolutional layer that we can just ignore them. Yeah, so then we flatten it by flattening. And can anybody tell me what flattening is? Any idea? Yeah, somebody in this area, they've been quiet. Anybody knows flattening? This area?
Matrix.
Translating? Yes, translating. Yeah, we can say it's translating, but basically converting your two-dimensional feature to one-dimensional. Another question, is the flattening operation, does it have any parameters? Yeah, is it something you learn? No, right? Is it a differentiable layer? Is it this is another thing to keep in mind. anytime you have things in neural network, in any sort of neural network, the important question to ask is your function should be differentiable. If it has parameters, and if it's not differentiable, you cannot do back propagation. Because remember how I don't know if we talked, they did like some intro to like gradient descent. Did we talk about gradient descent in previous sessions? No, maybe it was mentioned, but I don't know if it went to depth. But yeah, in order to be able to do gradient descent, you need gradient, which is basically derivative. So you can only use function if function has parameters, it has to be differentiable. Otherwise, everything fails. But yeah, this flattening operator is not it doesn't need any parameters. It's just a reshaping. So you don't need you calculate the derivatives here. You just reshape the derivatives too, and then go back to the previous layer. I think something like that happens. I haven't looked into the detail, but I'm pretty sure. Yeah. Anyways, but the key thing it took me so long to get to is the fully connected network even from yesterday had 160,000 parameters, whereas this has only 13,000 parameters, right? So this is 10 times less parameters. So this is, in terms of just the number of parameters, it's 10 times less, and it'll still take time to train, because it may take the same time, or this may even take longer. Why? Because does anybody remember? I mentioned earlier, even though it has less parameters, why would this take longer to train? Sorry? No, actually it's the same. There's 2 dense layers and 2 convolutional layers. Computation, yeah, that is correct. But why is there more computation? Yeah, right. The convolutional operators still have to be applied across all signal and all channels and whatnot. So even though the filter itself is just 3 by 3, or in one dimension, like 3 by 1, right? You still have to apply it over the entire image or the entire signal. So the number of computations you have to do is still large. But in terms of like stability of your gradients and training and everything, it's okay to take a little longer, but having less parameters makes your training like better and more stable, particularly with really large networks. Yeah, this is such a small example network, so here it wouldn't matter what you did. All right, we have just discussed the first important part about let me drink some water. Let me check what page I'm in. So okay, I should probably speed up just a little bit. So I'm not going to go through this too much. And one thing that I like to quickly mention is I borrowed a lot of these, particularly these images and the ideas from this book. I don't know how familiar you are with. I think it's in the NAAMII website as well. You can go and you cannot download the entire book, but you can download individual chapters. You can print them as PDF. So this, in my opinion, is one of the best books for particularly deep learning, not all ML, but deep learning, slightly more theoretical and more based on fundamentals. Yeah, but essentially, so the sparse connections. So like I mentioned, in the dense layers, we have something like this where every output is connected to every input. So if we look at X3, which is an input, and this S's are part of the first hidden layer, this X3, the input, is connected to all of the outputs of the first hidden layer. But on the convolutional layer, here I believe we have like a 3 by 1 kernel. That's why it's connected to 3 things. So X3 is only connected to three nodes in the first hidden layer. Yeah, sounds good. This is what sparse connection means. But another important thing to remember is despite having sparse connections in just like one layer, but as you go deeper, the connections do start becoming global, right? So this is it's flipped here. This, or you can look at it anyways, but so in the first this G3 in the second hidden layer is only is connected to H2, H3, and H4, and is influenced by these three. But because these three are influenced by X1, X2, X3, and so on, so as you go deeper into the network, your features do start becoming more global. And this idea is called a receptive field. So receptive field of, at hidden layer 2 is like the entire input. Obviously, in a larger network with where your data dimension is higher, you wouldn't have, just in the second layer, you wouldn't cover the entire input. Your receptive field would not be that deep, but your receptive, the idea is that you should make your receptive field in the final layers. Your receptive field should be as big as it should go all the way to the entire input, because at the final layer, you should have a pretty good understanding. You should reach a point where you start to understand the entire image. And that's why, the receptive field should be large enough by that point. That's why you should construct deeper networks with these convolutional layers, because if it's not deep enough, then your receptive field is too low and your performance might suffer. Okay, let's look at, actually these are the filters that were actually generated in that EKG example. I trained trained a model, and these are some examples. The first layer is some filters from the first sorry, the first row are the filters from the first layer. And can anybody tell, can anybody tell me, okay, first this one, what do you think this filter is doing? Can anybody tell me? Anybody has an idea? or maybe this guy, the third one. So I've color coded the negative values with green and the positive with this, I don't know what this color is, brown, I don't know. But anybody has any idea what maybe each one of these filters may be doing? All right, I will tell myself. So this one actually is rather, it's not really doing much, maybe because it's all like negative values and there's not a big difference. Sorry, some idea? Yeah, that's correct. The last one is like an edge detector. Why? Because this is a stronger positive value and this is a stronger negative value, and here it's almost zero, right? So this will do edge detection. This maybe does a little bit of smoothing. It's not a symmetric Gaussian, because if it was Gaussian, it would be the filter would be sort of more symmetric, even though it's just three values. It's not symmetric, but it's still, this is gonna do smoothing, and it does one more thing. What does it do? What are the values here? All values are all. So what is this gonna do to the signal? It's gonna flip it, right? So gonna just make it negative. Why? I mean, I don't know. That's what it learned, but I have some intuition, which is that we can see in the examples. I'll show you what it actually does to the signal, but because we remember ReLU, right? ReLU is just activates only in the positive values and deactivates in the negative values. That's why some filters should obviously like flip the signals and make it negative, because the ReLU only responds in one direction. You need to have these filters flipping things all the time, because otherwise, imagine a situation where all your your filters just produce negative values. That would just be crazy, because this ReLU would never, you would never learn anything, right? Yeah, we remember ReLU from yesterday. Yeah, Yeah, the rectified linear unit, which somebody asked me a very good question about. Oh, it's just like negative below 0, and how is it really non-linear? That was a very good question. So so these non-linearities, even the small non-linearities influence things in that way. In the second one, oops, actually, I think I made a mistake. I probably just copied this and did not update the value. But the second one is just not doing anything. For instance, this is an example. I believe this is practically 0, right? However, with the second layer, this is not the full picture, because in the second layer, the filters are of size 3/16. Can anybody tell me why the filters in the first layer it's 3/1, in the second layer why is it 3/16? Sorry? That's not true. The 3 is the filter size. It doesn't have anything to do with input. You're correct about, well, you're a little bit correct. The 16 is the, let's go back here. Correct. Who said that? Can you raise your hand? Yeah, thank you. Somebody in the back there said 16 is the number of channels. If we look at the first convolutional layer, it's the number of outputs is 16. So that's why in the second layer, the filters have to convolve across not just the XY dimension of the image, but across the channel as well. So your filter is going to be, in this one-dimensional example, 3/1 times 16. Or you can say 3/16 if you just, to reduce that 1 is not relevant. Yeah, that makes sense to everybody. Yeah, so obviously it's not easy to visualize a 3/16 matrix. So this is not the full picture, but so here, this being 0 means this for this particular filter and for this some particular channel, this filter is not interested in that channel. That channel hasn't learned anything interesting, so it just ends up learning, making it 0. Basically, 0 means there's nothing interesting to learn. Yeah, sounds good. Okay, let's look at now what the results look like from the layers. So we have an example original signal, and this second one. So okay, if somebody can, this is the one. Is it this guy? No, never mind. So here in the second one, this one, top right, let's not say second, but yeah, but can anybody tell me what's going on here and why it is the output like this? Somebody said inverse. Who said inverse? Can you tell me, stand up and tell me, if we can pass the mic, it'd be great.
I think we were using all the negative values.
So yeah, it's not all negative, but the first 2 terms are strongly negative, and even this is just a little bit positive. So overall, this will be strongly more negative. Yeah. And there's a little bit of edge detection because of this and this as well, but more so this is just flipping, right? That's why you said inverse.
Yes.
And okay, it's flipping. That's why we see these peaks, negative peaks become positive, right?
Yes.
Why are these guys 0? Why is it 0 in a lot of other parts? Anybody has an idea? Railu, who said Railu? Can you pass the mic to her? Or back?
Yeah.
Yeah, go ahead.
Kernels mostly negative.
Yes.
So values will be in the negative part, and really will just
ignore
him,
yeah, make it 0, right? It's all 0. That's why the positive parts are all 0. Yeah, thank you. So this one here, now can anybody tell me what's happening here in this bottom left? Yeah, who has an idea? So let's just look at the filter first. What do you think is going on in the filter? We already discussed this in the previous, we had a similar example. edge detection, correct. Why now? Okay, so that means edge detection is happening, right? So it's responding pretty nicely to these like sharp peaks, right? Here and here. What's happening here in the middle, all this fuzzy stuff, all this noisy stuff? Who has an idea? Okay, again, back to your signal processing, whatever, Fourier transform and all that world. I'm sorry for the other non E and computer engineering people, but you'll understand. Even I think folks who have taken calculus, this should make sense. Another way to think about the edge detection is also as a differentiator. You're taking local derivatives, right? And edge is there's a derivative because there's a change, right? That's why an edge detector can also be thought of as a derivative or a gradient detector, or derivative operator. So you could have in 2 dimensions, you would have your derivatives would be partial, right, across x and y. In 1D, it's just dx, or rather dy, the signal by dx. But what do we also know, as let's say, as opposed to the Gaussian operator, the Gaussian doing a Gaussian, we again from our signal processing world, if we remember, derivatives are inherently more noisy. If we've in your E class, if you've tried to, if anybody has done analog electronics, you know how with analog electronics you can make a derivative operator, like with circuits, and an integration operator, right? Your integrator always smooths and your derivative always makes noisy, right? And if you've ever had experience trying to do work with that kind of stuff, your derivative is always causing problems. Your derivatives are exploding, making a lot of noise. And oftentimes, particularly in classical signal processing, when people did apply a derivative operator, they would also smooth it by using Gaussian blurring. So this really noisy bits are a result of this derivative. So you can see here, even the original signal, there's a little, there's a bit of a like fuzziness, but it's accentuated a lot because of this derivative operator. In the final one, not very, I think it's just more flipping, but not much. Yeah, it's a little, so yeah, it's a little, there's not much interesting happening, but I'm a little surprised that, because this is very strongly negative, why are some of the, anyways, the ReLU, but yeah, essentially this is how the layers operate. And now let's look at layers responses in layer 2. So in layer 2, things get a bit complicated. It's not easy to make sense of what exactly is happening, because as we said, the filters are cross-correlating in the image spatial dimension and also across the filters. So it's not just, a filter is not responsive to just one signal. A filter is responsive to how many signals? 16, correct, because that's the number of channels in the first hidden layer, right? That's the number of, so, it's quite interesting. This first one is definitely a combination of like 2 sort of things, right? It's sort of these, it's picking, it's like, it's a, it has picked up the flipped signal, right? And it has picked up this sort of noisy signal from here as well. And it's some kind of combination of maybe like this guy here and maybe this guy here. I mean, I'm just speculating. I didn't look at like the exact numbers in detail, but the main point to understand is in layer 2 now, we're starting to build much more complex features. We're responding to much more interesting things than just like edge detector or something. This one, a lot of it is just going to be 0, because now we have a lot of channels and a lot of responses. Some of it's just going to be nothing. Here again, this is interesting. It is a combination of a response to this sort of flipped signal and also this not flipped peak. So it has both the high, the negative peaks here, and it has also the positive in this positive direction, right? So this is quite interesting. It has essentially picked up both the negative peaks and the positive peaks in the same signal. So you see, these signals are doing these really interesting combinations of like features, and with the added ReLU, it's always doing something non-linear as well. It's not just doing because it's making everything that's negative 0. Sounds good. Any question here? Yeah, I mean, I actually found doing this really fun. I encourage you to try this sort of stuff as well. Because we build these networks and train models and do testing and all this, but we never look underneath what's going on. So this was actually quite fun for me as well. Like I hadn't done this kind of stuff that much, so it was quite fun. So I encourage you to try as well, and I think it definitely helps you understand the whole thing much better. And you obviously cannot do this in a very, very deep network with like 20 layers, and if you start looking at the 15th layer, okay, I don't know, you can still do stuff, but particularly with these simple problems, I think it's easy to parse what's happening. Few more examples again. This is quite interesting. Like it has it has picked up some peaks, but it has ignored some. Again, I don't know exactly how that's happening, but yeah, it's quite interesting. I'm guessing what may be going on is that if you look at the peaks here, this one is a little bit lower, and these are all like a little bit higher, and it sort of seems to correlate with these peaks, but maybe this peak was not high enough. That's why it got cut off by the ReLU or something. I'm not sure, but yeah, again, more interesting combinations of features from the original signal. Okay, now maybe I'll pause for some questions. Remote people as well. So does everybody understand why we have combinations of features in the second layer, combinations of features from 16 possible signals? Yeah? Yeah? Yes? No? So you can actually, and I'll actually I think talk about it in the next session. You can reuse this convolution without going across the features as well. It would be kind of particularly for this. So there are operations that sort of separate out this convolution across the features and the spatial in the XY dimension into two different parts. They're called separable convolutions. We'll talk about it a little bit as well, but in 1D, sorry, not in 1D, but yeah, here these convolutions, and actually this was something it took me. I always had to remind myself to think about, particularly the convolutions in the second and the third layers. I had to keep reminding myself about this fact that you're doing this cross correlation or convolution not just across the image XY, but across the depth, the channels as well. Yeah, sounds good. Yep. Yes, please. Yes. Yeah, that's a very good question. Yeah, it's extremely popular in images because images are just naturally organized in this sort of like two-dimensional grid, right? But it doesn't have to, yeah. So any sort of data where you think there's like this hierarchy of like features that you can build from local to global. If you think that's a useful thing to do, then you can use convolution. So sometimes that may not be the case. So when I when I used convolutional network for this, the performance was not too different from the dense. It was actually the same, but obviously you get it for much less parameters, so it's nicer. But for obviously another very simple example is videos, which is just an expansion of image, right? So video is just image across time. So you can treat the time component as another dimension, right? So just like you have RGB channel, you can stack the time dimension as channels, or you can even make 3D input. So you have you can do convolution in 3 dimension as well. Well, in fact, any dimension, but in real life, you know, as you increase the dimension, it gets harder and harder. It gets more messy. But so videos, obviously, good example. So in time series signals, these days, most people mostly use this thing called RNNs, LSTMs, which we'll also learn about today. But again, it depends on what kind of time series signal do you have. So if you have a time series signal that is like rather sort of there's like some sort of non-linearity to it. Like you don't, let's say stock forecasting, right? You don't know exactly, there's no fixed pattern with the stock forecast signals, or I don't know, well, temperatures are periodic, weather's more periodic. So in this sort of situation, you know, it may be harder to use convolutional, because convolutional networks are looking for reliable, repeatable patterns that it can understand and, you know, accumulate and build you know, features. But with something like, let's say, this is a good example again with you know, and my colleague coworkers, we work with like time series data of like the heart again, but images. But there, because the heart, you know, moves in a periodic fashion, the images are also of periodic nature. So there's like definite temporal patterns. So I think in that sort of in those situations, you want to exploit it using convolution. But yeah, but you can use it. You can use it in time series as well. It may work, but you know, we don't know from the beginning whether it will work or not. Yeah, people use it everywhere. People use it for NLP. But again, you know, like I said, with NLP nowadays, the more successful models are a little different. They're called RNNs, LSTMs, or even transformers. Yeah, so yeah, that's the answer to your question. So some boring stuff now, but I won't go too deep. But we, you know, we already saw what the convolution operation works roughly. This is just sort of like the formula for it. I didn't include formula for the continuous one if you've seen it in like your classes before, but in you know, for discrete, it's just, you know, something like this. Let's just look at the second one, because this is more relevant for images and 2D images. So yeah, so basically let's this is the formula to do convolution at one like location. Let's say I is 0 and j is 0. That's the first, you know, point in your image. And k is your convolutional kernel, and I is your image. And the output at ij is just defined by this, which is just the cross correlation element wise multiplication and summing that we did, right? So your the k, mn, the I and j are fixed. I is 0 and j is 0, and your m and n varies. So m and n varies. Let's say it's a 3x3. So you know, it'll go from 0 to 2 and 0 to 2, and you know, you just, yeah, this makes sense. It should be pretty simple. Technically, the one thing, maybe in some notations, you will see that this is written in a different way, where the this k, the ij is on the k and not the other way around, with a minus I minus j here. But this just notation is simpler, and it's sort of more preferred. But if you see slightly different notation somewhere, yeah, it doesn't matter. It's not a big deal. Yeah, I have a recap of this. We already spent a lot of time on it, so I'm not going to go through it. But yeah, basically, this just follows this definition of element. Yeah, if we want to go at 0, 0, just go to 0, 0, I is 0, j is 0, and your m and n varies, and it's just essentially this element-wise multiplication. Yeah, I'm not gonna spend too much time on this. Okay, what does this code look like? I really wanted to show you this, because nobody writes their convolutional code anymore, because it's all there in your TensorFlow, PyTorch, whatever. But actually, the convolution, it's such a simple operation, right? If you look here, if you can understand this Python code, you just have your shape of the kernel and the image. Yeah, literally, you go from one. So I'm doing this for the entire image. I'm doing this one because yeah, well, I don't know why I have one. Maybe that was not necessary. Oh, okay, I know why. Because you have to reduce the size by 3. So yeah. So yeah, essentially, for every position, you grab the image, the 3 by 3 portion of the image at that position, and then you just do a element-wise multiplication and sum it. So it's really simple. It's just this. Obviously, when this is implemented in your neural network libraries, I'm pretty sure it's not a silly code like this, or it's something like this, but it's compiled with binaries and whatever, optimized binaries with C code or something like that. Because obviously in Python, doing this is pretty slow. You would never do this. You would use a optimized library to do something like this. But I just did it just to demonstrate what this looks like to you. And I actually took this image and I applied that example using, I made like a horizontal edge detector and a vertical edge detector, and I just combined them, so you can see what the output of these simple edge detectors and convolution look like for 2D images as well. So yeah, here you have horizontal edges, here you have more vertical ones. Yeah. And this is just a absolute value summation of the two. Pretty simple stuff, but as you can see, even something so simple, you get like a pretty nice outline of the filter of the flower, right? And this could be pretty useful for the networks and or other purposes. Yeah, any questions on these convolution things? We've already talked about it quite a bit, so I hope you guys are pretty good by this point. Okay, pooling. I think this is sort of like the last important thing to talk about before I try to wrap up. Yeah, pooling is a way of reducing, the dimensionality of your image in the spatial space, not the feature space. Remember, we have the 112 by 112 times 64 we saw earlier. This is so. And this particular operator is called max pooling. And what you see here is it takes a 2 by 2 region and it just outputs the maximum of that 2 by 2 region. So it's 20 here, 30 here, 108 here, and 33 here. Yep, pretty simple. Any questions here? So this is just a way of reducing the dimensionality of your input data. Of course, I did this in 1D as well. I'm just showing this for 2D. You can do a different kind of pooling. Another question, is pooling, are there parameters to pooling? Is a pooling a differentiable operator? Who knows the answer? Any guess? Is pooling a differentiable operation? Yes, no? Are there parameters to pooling? No? Yeah, what do you think? Okay, are those differentiable? Do they have parameters? Sorry? Yeah, there are no parameters in pooling, and yeah, there are no parameters in pooling. But with average, but the way you construct back propagation will probably be a little different for each of the pooling, but obviously you don't have to write any of those, so you personally don't have to worry about it. But again, just remember that these are not these don't have parameters, and these are layers that don't need to be differentiated. So here in this example, so just pay attention here from here to here. So most of the values are same, but they are, like they're perturbed a little bit. They move around a little bit. So as you can see here, the 20 comes here and the 30 goes here. The 108 was here, it goes here. Any questions? Size of the pooling, this filter, the operator? I didn't quite understand, sorry. Size of the pooling? Oh, strides. Oh yeah, so here I don't have any stride. It's a stride of 1. Well, actually, maybe this is 2. Yeah, this is sort of just the default. So another, yeah, actually, yeah, you're right. There is a stride, by which it means you do this and you skip and you go here. You move by 2 points in X. Yeah. Another way of doing this would be without any stride. So you do this here once, and you do this for this box with 20, 30, 12, and 0. And there the output would also be 30. And here, so we don't want to, of course, sometimes you want to do this with a stride of 1, but what would happen? I mean, can anybody speculate why a lot of times we don't use stride of 1 and do 2? Generalize? Reduce the dimensions. That's the correct answer. Yeah. So if you'd use a stride of 1, you wouldn't really do any reduction to your dimensionality. But by having this stride, like skipping, yeah, you just, yeah, you basically halving the dimension in both directions. So thing to note here is going from this example to here, there was like a lot of perturbation in values and also the position, right? All of these, the 20, 30, 108 appeared in different location, but the output is still 20, 30, and 108. There's a change in the 22. So, it was 33 here, the maximum. Here it's 22. But for most other cases, the values have been preserved. Can anybody tell me what this property is? Any ideas? Yeah, I saw a raised hand there. Translation invariance, correct. So yeah, this is and why is, again, since you mentioned translation, why is translation invariance important? We can't hear you, so unless you use the mic. It's yeah, please go ahead.
So when you have a like certain degree of translation in the input,
yeah.
So let's say we have a like 10 pixel of translation in the input image.
Yeah.
So when you apply those, it will give us a similar output,
yeah,
which will help us to detect task that we are going to do.
Yeah, that is pretty correct. To just give an example for this, let's say you're trying to detect dogs or cats. Well, if your dog has shifted a little bit, it's still a dog. It's not a dog. It's not that it's not a dog anymore because it's in a different location. So your classifier should be translation invariant. And this operation really helps with that, because your activations have moved a little bit around, but you're still getting the same output because, and this is really handy property. You're getting two things with this. One, you're getting dimensionality reduction, and two, you're getting translation invariance. You're also a little bit invariant to noise, not just translation, right? Because there was 20 here and some other values, but as long as the maximum remains the same, it doesn't change. It's fine. So it's, yeah, question? Is there a mic nearby?
Hello. Hello. So since we are only considering one numerics out of 4, are we not losing information? Since we are only taking maximum of that particular thing.
Yeah, that's a very good good question actually. Yeah. So if we had only okay, let's say you see an image of a cat, right? At the very end, the classifier has just summarized there's only one output. It's a cat. Of course, you've lost a lot of information. You've gone from a 512 or by 512 image, which is of 500 by 500, which is of dimensionality 250,000, to a one-dimensional signal. Let's say it's a cat, no cat detector, to just cat. So obviously you're reducing the information, but the whole idea is you have to reduce the information in an intelligent way. Let's say you take this 500 by 500 image and you just take the average, take the mean, and tell me the output is 108. What does that mean? It's pointless, right? So the whole idea is obviously you want to lose information, but you want to lose irrelevant information, but you want to keep only the relevant information. That's why we're reducing the dimension. That's why in the end, we only have, if it's a binary classifier, single or 2 output. And if it's a multi-class classifier, we have, let's say, we had like 9 yesterday in yesterday's lab, right? So very good question, but yeah, makes sense. Huh? Yeah, so yeah, you want to throw away useless information. You want to throw away noise. The fact that this dog has shifted 10 pixels, like he said earlier, it's not relevant, right? It's still a dog. So yeah, you want your network to be responsive to, you want your network to be responsive to things you care about, and you want the network to ignore things you don't care about. But let's say you're building a classifier. I mean, this is the whole crux of your ML. Like you want your network to learn interesting things and ignore uninteresting things. You want to, again, in this cat example, let's say you take image of the cat outside and inside. Why is it relevant? We don't care. We just want to know if it's a cat or not. We don't care if it's raining or sunlight outside or dark inside. Again, that's irrelevant information. So your network has to be invariant to, let's say, brightness factor or lighting conditions. We'll talk about that next session with face detection. I'm going to talk a lot about face detection. All right. Yeah, but very good question. Yeah, that's really important too. Okay, just a quick summary. Just like you saw with the dense layers, the building blocks of convolutional layers are also extremely simple. The only difference is the convolution operator, which is still linear. Again, please remember, there's nothing nonlinear about the convolutional operator. It's still a linear operator, right? the again, only nonlinear thing is the activation. I mean, the max pool is kind of nonlinear, but we don't, back propagate or anything like that with it. But yeah, maybe I don't want to. Let's not get into this. But yeah, most things are linears, and still the biggest nonlinearity is the activation, the ReLU. Okay. Maybe I will ignore this a little bit. We've already, talked about these network diagrams and, how there are the different layers, and there's a reduction of dimensionality from, layer 1 to 2 to 3. But as the spatial resolution is decreased, right? Another crucial thing to remember is we're reducing the spatial dimension, but we're increasing the feature dimension, right? So we're doing max pooling and decreasing. This is extremely common where you decrease the spatial dimension, but you always increase the feature information because you want to capture rich features and you want to capture a lot of them, but with in smaller and smaller form factor. Yeah, 2x2 max pooling features. Yeah, you've seen this plenty of time. I'm not gonna spend too much here. I wanted to spend a little bit time on this, but I think I'm just gonna quickly go through this and maybe we try to do this in the lab today. So this is something that is really helpful for me to understand and like count. So there's a way where you can count the number of parameters. And why is this counting important? Because when you build these models in TensorFlow or PyTorch, you can do model.summary, right? Do you remember model.summary from yesterday? So the summary will show you the number of parameters. And understanding how this number of parameters come about will help you understand the network. Sorry, I have a bad throat. Will help you understand the connections in the network. So just quick examples. In the first one, we have 64 filters times 3x3. That is the kernel. That is the kernel size. And what can anybody tell me what this 3 is? This times 3 that I have. RGB, wonderful. And what is this plus 64? Bias. Yeah, you guys are pretty good. I don't need to teach you too much anymore, I think. Yeah, this second one, same thing, but now, we have in the same layer because we have two convolutional operations, 64 plus 64. And same thing. It's in the second layer, we want to have 128 features. That's why there's 128 filters times 3x3 times, why is this 64? Channels where? In layer 2 or layer 1? Layer 1, wonderful. And that's what you get here and so on. And now let's just look at fully connected 6, right? Fully connected 6 it gets flattened, but look at this, the number of parameters, 7x7 times 512. That's what you get from flattening times 1024. I mean, this is crazy, 102 millions. So this is, even though this looks like a big convolutional network, most of your parameters are just here in these fully connected layers. So it's again, these fully connected parts that are most parameter intensive, and the convolutional parts are actually not that heavy in terms of parameters. Total is 138 million, but just this one layer has 100 million. I mean, which is kind of crazy. Again, you'll see this in lab, but yeah, we saw this yesterday already. I mean, it's pretty easy to construct these networks and train them and so on and so forth. Yeah. All right, I am done. Questions? Remote people as well, please. I think we're out of time, so let's just a few questions. Because I think we did pretty good question answer in the presentation itself. Yeah, here. If somebody can pass him the mic, that would be great.
So essence of CNN is we keep on decreasing.
Yes. That's extremely standard. Yeah.
So the number of channels and the shape of filters, are they hyperparameters, or how do you decide?
Yeah, that's again very good question. Yeah, they are. We don't know a priori what's the best ones. For instance, the convolutional, the kernel size. Uh, back in the days, people used to use different sizes, like they used 5x5, 7x7. Obviously, obviously, those are, the bigger you make, there's more computation required. So that's a trade-off. But another thing to note is, they realized that doing two 3x3 convolution is the same as doing one 5x5 convolution. So why that's why, these days I have not seen too many papers where you have 5x5 convolutions or 7x7 convolutions, because you can just do like a couple 3x3 convolutions, and you do it once, it's 5x5, do it again, maybe it's 7x7. Does that make sense? So typically the kernels these days, no, people don't use too many others. But the number of features is definitely a hyperparameter. Yeah, but again, you use this principle, this which he asked earlier, right? You reduce the spatial dimension and you keep increasing. And the VZZ is like this really like standard, because they do it in like extremely simple. They have like this heuristic where they're always doubling the number of features, right? You could use this. This is just another heuristic. It doesn't have to be that way. Yeah, but these are all hyperparameters. We cannot. So okay, quick question for you all. For you maybe, because since you asked, what is the difference between hyperparameter and parameter? Why is a hyper there in front of?
The parameters are, I guess, the learning parameters are weight and biases.
Yeah.
In general, but the hyperparameters basically gives you the architect in some sense.
Yeah.
Like, yeah. So how you build a neural network is how what a hyperparameter
Yeah.
will decide.
So yeah, that's correct answer. And another way to say the same thing is you can train the parameters using the optimization, right? You're optimizing the parameters with your neural network training. You're not optimizing the hyperparameters. So that's a crucial difference. But is there a way to optimize hyperparameters as well? Can you optimize hyperparameters? How would one do it if they want to do it? Sorry, who? Somebody in the back? Yeah, that is a good answer. Yeah, that's correct. Basically, you just build, a big set of potential hyperparameters, and you keep testing it on some validation step and see which gives the lowest error. Ideally, you want to do cross validation on this. I'm not going to get into cross validation, but not just a single validation. But the difficulty with neural network is that it's so hard. It takes so long to train these models, and your hyperparameters could easily be thousands, millions, right? Because if you want to optimize every one of these things, it'll take forever. So oftentimes, practitioners use a blend of just past experience, intuition, and some testing on validation set. Yeah, but that's correct answer. Yeah. Cool. Any more questions before we take a little break? Remote people? All right, I think this is it.
Excuse me.
Oh,
Can we see?
sorry. I didn't get it. Oh, okay. Yeah. Sure. Here.
This is for discrete convolution. But while we are changing discrete anything.
So yeah, I mean obviously the infinity is the correct formulation of the problem, right? And you can have infinity in finite discrete signals, and you can have infinity in continuous signals as well, right? Infinity is not exclusive to continuous, so that's number one. But yeah, but because both your image, in fact, you do have to do it till infinity, but because you get all zeros, it's pointless to do it till infinity. You only do it in that domain where it matters. Does that make sense? It is technically till infinity, but practically, since it doesn't matter outside of the domain, it's all going to be zero. Yeah, that's the answer. Cool. I think I would like to end it here, and we have more topics in the next session, and there's the lab, so you are going to be busy. All right. Thank you, everybody. Take a little break and we start again.